First of all, welcome all of you. Third day or last day of our conference. And the next talk is Cellular Automata, computing from the group up, count up. Speaker is Professor Lent. Professor Lent is the Frank M. Freeman Professor of Electrical Engineering at the University of Notre Dame, Indiana. Professor Lent received the bachelor degree in physics from the University of California at Berkeley and his doctorate in solid-state physics from the University of Minnesota. Professor Lent has been a member of the Notre Dame faculty since 1986. His research in the area of quantum device and molecular scale devices. Welcome, Professor Lent. Now you can start your presentation. Professor Lent.
Thank you. I'm going to share my screen.
Sure, sir.
Thank you to the organizing committee for inviting me. It's a pleasure to be able to talk to you all. So I'm going to be talking about this work done at largely at the University of Notre Dame, but with some other international collaborators. I've listed just some of the people who have contributed mightily to this work in electrical engineering and chemistry, and some of our key collaborations. So what I'll talk about tonight is, or this morning, first the challenge that this field is a response to, and then I'll describe quantum cellular automata, the basics, and I'll end up talking quite a bit about clocking, and then the various physical realizations. I'll talk a little bit about circuits and architecture. And then I can't help myself but to talk some about thermodynamics because it's kind of a driver for this. And then with the remaining time, I'll talk about molecular QCA and our attempts to move towards that. So the challenge is to have a new basis for electronics. And what we're looking for is general purpose digital computation. We of course want high speed and high functional density. We'd like to be able to have a technology that scales down to the ultimate limits, and the ultimate limits are arguably single molecule devices for the simple reason it's hard to construct pattern matter at a smaller scale. So that's probably the best we can do. We of course have present electronics based on CMOS, complementary metal oxide semiconductor transistors, and it's been wildly successful. That there have been challenges doing the scaling all the way down, although it's always very impressive. And the biggest challenge is power dissipation. So it goes back to Konrad Zuse's paradigm in the 1940s, who also played a significant role in the history of cellular automata. He was the first to use binary numbers to encode information and represent the digits, the binary digits, as the on or off states of a current switch. His current switch was a telephone relay. So his adder weighed more than 100 pounds. The basic idea here shown in the garden hose version is to encode information by the flow of a current that can be turned on or off, representing a 1 or a 0. You also need the flow through one switch to turn another switch on or off. And that was the paradigm that began with these electromechanical relays, which were replaced by vacuum tubes. The vacuum tube triode was and sometimes still is called a valve. And then if you're like me, if you're as old as me, you can remember transistors being little cans, solid state transistors, and then the modern CMOS integrated circuit. And this has provided just this exponential downscaling that we have all enjoyed. There are problems with shrinking the current switch. They come in a few varieties. The valve shrinks also, so it becomes harder to get a good on or off. That's why we have FinFETs and gate wraparound and multi-layer wraparound. So different ways of allowing a charging on a gate to constrict another current flow. The current becomes small, the resistance becomes high. It's hard to turn the next switch, and you can run into issues with the quantization of charge. But most importantly, power dissipation threatens to melt the chip. So we'd like to continue this downscale and be able to get down to single molecule devices, but it's going to take some new thinking. This is just a slide perhaps you all have seen many times, this sort of slide where we have Moore's law it's been doing quite fine in the number of transistors. The performance has kind of bent over, the single thread performance. And the increase is perhaps mostly due to very clever tricks. The frequency, some of you will remember when you bought a computer based on the frequency of the processor, but that stopped increasing in the early 2000s. And the reason was the power dissipation hit 100 watts per square centimeter, and it's just hard to get much beyond that without heroic means. And we may go to heroic means like water cooling and fluid cooling, which is where we used to be. We used to cool things with water and then Freon, but it was nice to get away from that. And that's really been the limiter that limits the frequency. The devices themselves would still work at much higher speed. So we're actually slowing them way down from where they would be to solve the power dissipation problem. So that's why we have to talk about thermodynamic fundamentals in a little bit. So I was intrigued by cellular automata from an early age, Conway's game of life. Ising models are one of the first things I programmed on a computer. Intrigued with lattice gas models. So the thought we began with was, well, there's something very appealing at that, having interactions only with the neighbors. Now we're going to have to deal with the fact that we can't connect to all these individual cells directly except at the edges. And the thought behind quantum dot cellular automata was, well, we're going to need to get down this small and this dense. We have to let the physics determine the rules, the cellular automata rules. So what does the physics tell you? Well, we've got two cells and we need them to communicate with each other, to influence each other so they can change each other's state. How can they do that? What's the physics that you can use? Well, you need a strong interaction. That is, we need something that's powerful enough. So what have you got? Gravity is too weak. The strong and the weak interaction are too short range. The direct spin-spin interaction is quite weak. You can get something like magnetic coupling. It works at a larger length scale, but the smallest, it's also quite weak unless you actually have exchange coupling, which means you've got current flowing again. So the candidate that we focused on was the Coulomb interaction. So electromagnetic, and it can be quite strong at the smaller length scales. So let's think about that. So you could do it, you could conceive of it all as dipoles, electric dipoles. It's convenient to put them together and form an electric quadrupole so you can have the same repeat unit. What happens? Well, neighbors tend to align just because I can't seem to point there. Neighbors tend to align because the little red dots repel each other. There it goes. So this electron is pushing that electron over there. So in this, we can think of this as a 1 state, and this is a 0 state, same interaction. The diagonal interaction, the corners anti-align, and that's basically what one has. So what happens if you make a regular array of these? Well, they kind of all influence each other to go into the same state. If you make a checkerboard pattern, then they are alternating with each other. But the problem is regular arrays don't produce very interesting behavior with the rules that physics gives you. So, well, if regular arrays don't produce interesting behavior, what about irregular arrays? Well, they do produce interesting behavior, as we'll describe more. And such irregular arrays look like they can do logic and computation. We'll have to expand on that. But it starts to look like circuits, like logical circuits, where bits are influencing other bits. And indeed, you can start to lay these out. I'll come back to this sort of thing, but make adders and the like by just laying these cells out and letting them interact. So let me broach it more formally and build in the clocking. So the idea of quantum dot cellular automata is to represent the binary information by the charge configuration of the cell. We'll keep it pretty generic. These antipodal cells will hold 2 electrons that are repelling each other. And they can be in this 1 state or in this 0 state. We'll think of these as the active dots. And let's suppose that we can control with another signal, which we'll have to describe, and pull them into this null state here. So we think of the active state as holding information and the null state as not holding any. So you have dots, they're areas of physical space that localize charge to integers. You have 2 mobile charges. You have quantum mechanical tunneling between the dots. That's what quantizes the charge, yet lets it move, right? The quantum mechanics, if you will, first blush provides the grease that lets these move. And you have some kind of clock signal that varies the relative energies of the active and the null dots. The clocking, which we'll spend a little time on, it allows adiabatic operation that'll get us lower power dissipation. It also permits active signal restoration, which means power gain, because you have to replace the signal energy from somewhere else, and you're replacing it from the clock. So if we consider this cell being in the 1 state, and this one is initially in the null state, when we raise the clock on that, then just the Coulomb interaction tends to move this into the same state. So that's the copy operation. We've copied a bit from 1 cell to its neighbor. What if it has more than 1 neighbor? So this one's in the 0 state, this is in the 1 state, this is in the 1 state. We're going to activate that one, let's say. Well, so the fields that are pushing, affecting this cell add, so the bits vote, you could say. So the 2 1s give you a 1 and override the 0. So that's a useful majority logic function, which you can think about as a programmable 2-input and or gate. That and the diagonal interaction that gives you a not is sufficient to do anything you'd like. The first of these that we've made, spent a lot of time on, The role of the dot was actually played by a piece of aluminum on silicon dioxide with little tunnel junctions. So that some of the capacitors are regular capacitors that couple this double dot, say, to this double dot to make a full cell. These are tunnel junctions, so they're very thin capacitors that are quantum mechanically leaky. They have a high barrier, but it's thin, so they can, so charge can tunnel from one side to the other, but the charge is forced to be quantized by the barriers. So you can lay those out and do the experiments and show the majority gate going through its truth table. They're all low temperature. The temperature we've been able to raise the temperature some. They're not low like quantum computing low, or like microkelvin, but they're a few Kelvin. This shows the clock. This is part of a shift register. So those have been made. And a number of these devices have been made. Wires or shift registers, inverters, and or gates. The majority gates, we've shown fan out and fan in, and isolation of the input from the output, and importantly, the power gain. And Greg Snyder, who fabricates these, my colleague, is working to raise the operating temperature using clever techniques for making the tunnel junctions. So one can think about this as importantly, this clocking occurring in zones. I'll show some other ways to think about it, but different zones that turn on. So these latch the bits at the input, and then this next level of computation, then the next one, and information moving around as it's being controlled by these clock signals that don't have to address individual cells, but address blocks. So let me just describe some implementations briefly. I've shown you the metal dot QCA. I'll mention the semiconductor ones, magnetic ones, a kind of CMOS analog, and then I'll later get more to molecular QCA. So the Cambridge group made QCAs in gallium arsenide with aluminum gallium arsenide on top. There's a two-dimensional electron gas underneath the surface, and this a well worked out technique of putting metal gates on top. You put a negative potential and it depletes except where there isn't metal, and so you form these dots. And also you can use this to measure the charge, and they showed functioning QCA cells. This Australian group made invisible dots by just, they were making little dots by implanting a few phosphorus donor atoms. And so you could see the gate, the actual dots are invisible. And they demonstrated that in silicon with phosphorus donors. Bob Walco at the University of Alberta does amazing things with a scanning tunneling microscope. So here you have silicon, a cleaved silicon that's passivated with hydrogen, and then he uses the tip to remove individual hydrogen nuclei, just protons. So he takes off one proton at a time off the surface, and what's left is a dangling bond that can act like a dot. So he's shown QCA cells, and he has an elaborate procedure for fabricating these. And these are all room temperature because they're at the molecular scale, 2 nanometers or so. So the energies scale up. Things get better when you shrink down. My colleague Wolfgang Porad's group, if you essentially change the positive and negative charge to north and south poles of a magnet, you can do all the same things with tiny magnets, permalloy magnets, and they showed majority gates and clocking and the like. I wanted to mention, so we came to this by thinking about, well, can we do something like that in CMOS, where the idea was to use make a dot from a floating CMOS gate. And a lot of the reason this works is because for low power is you're just moving a charge from here to there and back. So we worked, several of us together on this sort of thing, and it turns out we kind of reinvented or rediscovered what's called adiabatic CMOS, where you have, instead of the key from the point of view of power is, instead of taking a charge from VDD and letting it go to ground all the time, you have two clocks that are opposite each other, and so you keep recovering the same charge. You never throw away charge. That turns out to be a pretty good idea. It's, comes at a cost of some reduction. You lower the power dissipation by reducing the frequency. That becomes more and more palatable because you're already reducing the frequency so much. So let me turn to say a few words about circuits and architecture, about which I'm not. Lots of people know a lot more about this than I do. So Conrad Wallace enabled a lot of this exploration by building this program, QCA Designer, which enables people to start thinking about, well, how would you do computation on a new basis without transistors, but with this sort of thing, layout, clocking, floor plans and the like. And that has been fantastic at enabling lots of people who are much better at circuits than I am to work that out. And there are a number of groups around the world and a number of groups in India that have been doing that and do serious things, put serious circuits together that are beyond my kin. But I really appreciate what people are able to do in exploring by construction this whole kind of circuit area, and also thinking thoughts about the clocking schemes. And I think this kind of, so start with the clocking scheme, think about that, and then decorate it with the circuit that you need. So think about data flow, think about that. That seems to me to be exactly right. And you can also start to see maybe there's an idea here of building cellular automata of the usual type at a bigger scale, aggregating these things. And that's a way to break the von Neumann bottleneck, to intermix computation with memory, in-memory computation. It's kind of computing in the wire, computing as you move the information. So bits moving and bits colliding with each other, that's all part of the same story. So those seem to me to be exactly the right way to start to expand thinking on this. So let me say a few words about thermodynamics, because it haunts us, because one of the big drivers is this heat dissipation. So in fact, the fact is that it raises the question, is there a fundamental lower limit on energy dissipation per bit? Is there a minimum amount of heat that must be generated to compute a bit? So we know that all our computers could be acting faster. They could be computing much more quickly, but your laptop would get too hot. It would burn your lap, and you have to take heroic measures to keep your computer cool. So is that amenable to a fix? To what extent are we pushing up against a fundamental law of physics that connects bits to heat? So that has a long question. That has a long history. Sorry, that question has a long history. Going back to Maxwell's demon, who was by first measuring states. There was a hypothetical being, obviously, who could measure states and then perform reversible processes thermodynamically to lower the entropy. Szilard and Brillouin argued that it was the measurement that caused a minimum amount of heat that needed to be dissipated, kT log 2, which is the heat associated with 1 bit of information, 1 bit of entropy. Entropy being a slippery concept. Landauer argued that it wasn't the measurement, it was the erasure of information that has to cause a minimum amount of dissipation per bit. This is called Landauer's principle. And Bennett pointed out that you could do, in principle, any computation without doing any erasure. So you could always embed something that erased in a larger framework where you kept that information and didn't erase it. So the connection, there's this connection between logical reversibility, by which we mean looking at the outputs, you could tell what the inputs would be, and physical reversibility, meaning you could run the movie of the physics backward. So that's still somewhat controversial, even though I would argue it shouldn't be, but it is. It's controversial in various circles, including my own department. So we came to this without necessarily having a dog in that fight, but looking at what happens, now this is, by looking, I'm talking about calculations of quantum mechanical calculations. When you see the clocking moving information across one of these circuits, the computation happens at the leading edge, where things that are in the null state are raised up, the clock goes high, and they change their state based on what's behind them. What happens on the downside of that wave, if you like, what we observe is that dissipation happens here when, for example, in this majority gate, a loser, this one lost the vote, right? So the vote loser, when that cell relaxes, then you get a burst of heat dissipation. It's true, you can watch it happen in interesting ways. I'm alighting over the physics underneath the calculations, which is quantum mechanics, the interaction between these cells, and so forth. But so with a shift register, you can go from the input to the output and see minimal dissipation, much less than kT log 2. If you have an OR gate, so you fix this to a 1, so it's A or B, then if they're both 1s, if both A and B are 1, you see very little dissipation. But if one of them is 1 and the other is 0, that loser will cause much more dissipation to the environment. If you, surprising perhaps, if you echo the inputs to the outputs, so I'm calling this Landauer clocking, the usual kind of clocking there, then you just do the calculation and you see, yeah, if you echo the inputs to the outputs, much lower in dissipation. But of course, you've got to carry along the inputs and decide when you're going to erase those. But it's just the case that it's the erasure part. When information is lost, you see dissipation. There's a way to get around that, but it's costly and has to be done, I think. But some people are quite enamored of this. you can do the what I call Bennett clocking. You slide the clock over and hold everybody in place and then run it backwards. So the losers, let's see, a loser, those are all winners. So the loser is just held in place with all his neighbors, and then you use the output to unzip everything. You can imagine doing that on a whole array, I mean a block, and calculating everything and then uncalculating it. You sort of latch the output. And then of course you got to pay the piper at some point. You have to erase the inputs. But if you wanted to get serious, and some people do, at squeezing out every last bit of dissipation, you could do that. So with Bennett clocking of an OR gate, you do see dramatically lower power dissipation. And how can we understand that? Well, let's step back a little bit and make an argument. So you've got some kind of physical configuration space, and you have a 1 or a 0, and it's helpful to think about erasure in this case as going to a null, not reset to 1 or reset to 0, which confuses things. So you have a time-dependent Hamiltonian, and the claim is if you're going to erase it, that you could take a 1 and turn it to a null, or a 0 and turn it to a null with the same process, the same Hamiltonian. So you have to use the same clock, the same machinery. Well, that turns out to be one of the things that just can't happen. Quantum mechanically, you can't go from these two states, both of them go to that state. This is the quantum mechanical operator that takes you from time t equals 0 to some future time. So it can't be that that time-dependent Hamiltonian would take you from A to C, and also would take B to C. That can't happen. The microscopic laws of physics are reversible. So if it looks like this, there must be something hidden from view. So there must be another degree of freedom. So on this z-axis here, so it looks like they're both going, but in fact, they're separating along another axis. Something else is changing. So what could that be? Well, it's got to be another degree of freedom. So the one you're focused on goes from 0 to null, or 1 to null, but the other part of the system must have a record of what this used to be. So in the circuits I've shown you, so you have a bit and you have a copy. And if you make a copy of it, then in the presence of the copy, you can erase it with minimal dissipation. So the other degree of freedom could be a neighboring bit. That's why the Bennett clocking works. On the other hand, it could be the environment. It could be the whole heat bath. So, but it's a physical system too. And so what you've done is the past of the system, the bit that used to be there, now has an imprint in the environment. There are two different ways the environment could now be, depending on whether there was a 1 there or a 0 there. So you've increased the number of ways the environment can be. How did you do that? Well, perforce, you must have transferred energy to the environment, and therefore expanded by a factor of 2 the number of ways it can be. Transferring energy while increasing the entropy, the ways it could be, is what we call heat. If it doesn't increase the entropy, and then we call that work. I wondered, well, can't we just show this is the case? So we did an experiment on a benchtop at room temperature. which was just charging a capacitor. It was surprising nobody had done this before. Let's charge a capacitor and let that represent the bit and do some of these operations. Now, the bit energy, the amount of energy you put into representing the information, has to be much larger than KT in a thermal environment. So the green here is the bit energy. But when if you erase it in the presence of a copy, and the slower you do it, the less energy you dissipate, or the red ones, you can dissipate much less than KT log 2, which is this line here. You can erase with a copy, dissipate orders of magnitude less than KT. If you don't have a copy, you can't do it. It generates, you end up dissipating almost the entire bit energy to the environment. So thus endeth the sermon on thermodynamics. So let me talk about molecular QCA in the time remaining, and I'll try to keep close to on time. So the role of the metal, in the metal dots, the dot was played by this piece of metal. In a molecular QCA, the idea is to use a redox center. It's typically a metal dot, but it can be other things. That can be, it's redox, it can be reversibly reduced or oxidized. We can add an electron to it or take it off without breaking a bond. So in chemistry, I'm kind of turning to chemistry. This is the field of mixed valence compounds. And the key strategy is use non-bonding orbitals, either pi states or d orbitals, to act as dots. You don't want to break a bond when you switch the device. That's counterproductive. So the good news is you got the strong interaction. The Coulomb coupling gives you strong energies, and a lot of the work is about designing the molecules to do this. What makes a good dot? What makes a good linker? By changing the linkers, you can vary the transfer rate by 12 orders of magnitude. And it starts very small. The Hartree time scale, which is essentially the time it takes to get from one side of an atom to another, is 10 to the minus 17 seconds. So you've got a lot of room to slow down and still be quite fast. And you want to finally be designing molecules for clocking. So just I'll get into this clocking by considering a toy molecule. This is a molecule that's got 3 dots, and it's actually got a mobile hole. So these are pi systems, and there's a hole that can be here or there or there. And they're radicals, so they in the real world they'd be very reactive. But in a computer quantum chemistry calculation, they're just the thing to get started. So here's the hole is present here, representing a 0. Excuse me. It's on the null, this lower dot, pardon me, representing the null, or it's over here. And these are the isopotential surfaces that come out of the calculation. And the idea of clocking then is if we can put these little guys where we want them and have a local electric field that either pushes it up, pushes the hole or whatever the mobile carrier is into the active state, or pulls it down into the null state, that's what we want to do. So you imagine here you've got some input and you've got a buried piece of metal. You've attached these to the surface. If you push them up, then they're active. If you pull them down, then they're in the null state. And if we now consider these buried clocking electrodes underneath, then you have a place where they're pushed into this active domain. They're now electrons, the little red dots, or they're in the null domain, or they're in this switching region. You don't have to have any current leads, and there's no need to contact individual molecules. These can be on a much larger spatial scale. So we do this calculation with buried clocking electrodes and just look at the perpendicular fringing field. They can be much bigger than the molecules then. So I'm now looking down on the surface, and the white area is just the calculated strength of the perpendicular electric field. And schematically indicated are the buried wires, and there are regions where the perpendicular field is high, and so it's pushing the cells into the active state. So now at a much smaller scale, we've decorated the surface with these QCA cells. If we zoom into the molecular scale, then what we see is this clocking wave going by, and we're actually solving the time-dependent Schrodinger equation here at every point, where every cell sees its neighbors and also the clocking field. So these are bits going by, bit packets. So the bit packets are now colliding to compute things, doing logic on the majority gate, and more complex circuits, right? So information is moving and colliding with other information to produce computation. You pull out and you have multiple waves going at the same time, a kind of deep pipelining. I think you get the idea there, information moving around. If you start thinking about these clocking wires, you can arrange the packets so that they don't overlap, so that they cross over each other in different phases. And Peter Kogi proposed, well, you just start with the floor plan, start with this clocking, somewhat like I was showing you earlier. Just make sure you can move information left to right, right to left, up, down, and you can store it in the circulating, so information can reside. And again, you're starting to see, it looks like maybe it's cellular automata of a sort on a different length scale. So all that was to say, it's not crazy to think we could clock molecules. I'll show a few molecules before my time runs out. So the first experiments we did with Tom Fellner in chemistry, so I say we generously, were double dots where one dot has ruthenium and one dot has an iron center. So they're unequal double dots, but he was very clever. He bonded them to the surface. There are these phenyl groups here that act as struts to keep it upright, and groups around to keep it insulated. So it's covalently bonded to the surface. And you apply a potential across there and essentially turn the iron into ruthenium, at which point the charge can transfer, and then you occupy the other, if you like, showing clocking happening at the molecular scale. And the signal is the differential capacitance, where we actually saw two peaks. We thought we might see one. The reason was there were counterions. These are ions, and so the neutralizing charge could settle into one of two positions. And the quantum chemistry verified that, yes, this should work, and you should be able to switch it at these kinds of fields. And what we could do in the computer then is ask, well, suppose we could just run with this. Could one of these molecules switch another molecule? And the answer was yes. Quantum chemistry, room temperature, the dipole moment of the driver molecule is sufficient to switch another molecule. There were several generations of these things, longer stalks. These are two ruthenium, so they're equal double dots, still have the tether on the surface, still have the two states. And that one, they're able to wash off the charge, the counterion, and see the switching signal where it goes click, clack. Tom Fellner also built 4-dot cells, although without feet to attach them. So, but we could do the computer model. Quantum chemistry showed, yep, one of these would switch a neighbor, which is what you want. Claude Lepin's group in France has been working on all kinds of different linkers. What makes a good dot? What makes a good linker? Alex Kendall can take these molecules and put them on the surface. This was really interesting to me because these two molecules have all the same atoms, all the same bonds, except this angle off that benzene ring was different. This, on the time scale of the experiments, delocalizes. This is strongly localized, and he could put both on the surface and see these kind of molecules unaffected, these going either on one side or the other. I will skip the details of this argument, which was, it would be good to be able to build the donor in. So I had a student who was good at all this chemistry. So he said, you know, I think I know how we can do this using boron cages. So 2 different dots and then a boron, which acts like a built-in donor. What the chemists actually made was slightly different, but it was based on the same idea, the boron cage here and these 2 dots. So this is now the 3-dot, kind of clockable, doesn't have feet. Let me just, so this is an exaggerated view of the nuclear motion when there's an electron transfer. It's exaggerated, so you see the nuclei respond too. So Eric Blair, former student of mine, did a fantastic job of modeling the electron coupling to the vibronic system and the environment, so we could see at the molecular scale questions of how much power gets dissipated. Let me just jump to this. So 3-dot molecules, this is a quantum mechanical calculation. The electron degrees of freedom are here. The nuclear relaxation is a harmonic oscillator here. And the dissipation, so I'm gonna just watch it, the clock go up and down, and it switches, and then switches back to the null state, and then it's into the opposite state, the 1 state. You're doing it quickly, and you end up seeing several kT log 2s of dissipation. If you do it more gently, or you have lower heat sinking basically to the environment, then you see the same behavior, but now with really small power dissipation to the environment. You can tell I'm worried about power dissipation because it's what makes our laptops hot. So I'll wrap up there, trying to keep on time, leave time for questions. So I hope I've perhaps at least intrigued you a little, that there's an interesting set of problems here. There's a way to use cellular automata ideas anyway with at least in the first iteration, irregular networks, but have local interactions. They're the interactions physics gives us. I think there's great reasons, and I'm delighted that people are exploring the circuit and architecture considerations. I've told you why thermodynamics actually drives all of your computing demands. It's why your clock speed isn't 50 gigahertz, it's just 3 or 4, because it could be otherwise. And interesting area where engineering and physics and chemistry come together to look at this, the possibility of getting down to molecular scales. So thank you for your attention.
Thank you, Professor Lent, for this interesting and nice talk. Now, is there is any question from audience?
Sir,
And,
can
yeah,
you hear
come.
me, sir?
Yes, Kamalika ji, tell me.
Yeah. Thank you, Professor Craig Lent, for this wonderful talk. We are amazed at this lecture. Like, it was combination of engineering, then CA, the abstract. We only know the abstractions of the CA. Now you implemented it to the molecular level. You show how chemistry, physics, electronics all are interacting together. And then the real problem of heat dissipation, how it can be solved to some extent. Really, we are amazed. And I thank you very much on behalf of the organizing committee to give us this opportunity to listen to you.
Oh, thank you. It's an honor.
I am not from QCA background, so I might not be able to ask you very interesting question. I'm just asking you some naive questions. So you were showing us that by using this kind of architecture, heat dissipation can be limited to a very low level. So is there any plan of developing chips based on this QCA models that you are developing, or like real life computer? How far we are from that?
Yeah, it's so the closest, as you might expect, the lowest lying fruit is the sort of adiabatic CMOS version of that, where and I think that has real possibilities. People have to be willing. The problem is you even there, it's the same CMOS, but you have to be willing to do a rather thorough redoing of your architecture, and we're pretty invested in the architectures we have. But it was very I think it's very doable to do that. We Notre Dame, my colleague Greg Snyder, has built considerable chips, microprocessors, and things that can play the Notre Dame fight song, things like that, out of adiabatic CMOS. The metal dots, I think we could do great. If you view those as prototypes, their problem is just they have to be cold. And as I alluded to, people are reluctant, to chill things unless they're quantum computers and can break unbreakable codes. So then they're willing to chill, but then can be quite. They've got their own challenges. So yeah, I would say it's certainly down the road. For us, we're looking at a possible future here and trying to figure out how to get there. And part of the excitement for me about seeing people work on circuits and architectures is it really does take new thinking about that. So it's very helpful to see what could you do? How would you reconceive of this? So I think that's terrific.
And can we totally avoid the one human bottleneck?
Well, seems like we're going to have to learn to try. That you could say that we're already making pretty big moves in that direction with GPUs. We're distributing processing and memory more. It's just a question of the granularity of that and how to take that to the ultimate limits, where it seems to me what ultimately you want, which is it's very much a cellular automata vision. It's the computational universe, if I can quote, the computational universe of interacting things that hold information and move information at the same time. So I think we need to get around that, and I think you could say, yeah, we are trying to get around that. I visited Intel a few years ago. This will date the time of the visit, and they said, well, do you have something we can make now that gets past this? And they listened and said, wow, we can't make that soon, and unless we can make a new generation every 18 months, we're going to have to close the doors. So he said, well, Craig, I'll tell you, the plan is we're going to start to put more than one core in and have more and more cores and see if somebody can make that work. So yeah, that's so we're trying to get there.
And sir, if this you are showing that the role of CA is only at the very basic level, that is how you are designing the molecules based, or you are designing the rules based on the molecule interaction, or the reverse way. So my query is, are these CAs, basically the CA rules, are they reversible in nature? Or is reversibility has any role in the whole picture?
Yeah, if you look at the classical cellular automata, most of them are not logically reversible, right? Things vanish all the time. I think it's a fascinating area to say, well, what if we're interested in just reversible ones? So things that are not logically reversible can't be physically reversible. They're going to have to dissipate. But it's all a question of degree, you know. I was trying to wave to the idea that, okay, so there's the kind of micro CA. We had to do that with kind of circuity looking things, but maybe there's a CA that sits on top of those, that has functioning units that speak to each other, and those could have different kind of rules, right? There you could engineer the rules. So if you had a kind of large grain cellular automata built on the microscopic cellular automata, now with the large grain ones, you can design the rules. You can't avoid thermodynamics, but.
Thank you, sir. I asked lots of questions. Maybe someone else will be interested to ask.
Okay, thank you, Professor Lent, for this wonderful talk. Yeah. Okay, just I have a quick question. So you are talking about minimum energy requirement per bit. So by QCA, can we achieve this always? This minimum, if you do computation through QCA, then minimum energy requirement per bit, I mean, is it achievable?
Yeah, so I set it up in the way it usually is phrased, to compute a bit. And the answer is that there isn't a minimum energy to compute. You can always, if you're willing to keep intermediate results, you can do any computation in principle that you'd like without there being a fundamental minimum energy that you have to dissipate as heat. As a practical matter, you're going to have to erase some intermediate results in all likelihood. And so it's not calculating the bit that is the problem, it's the erasure of results, whether they're intermediate results or anything. And so if there's a loss of information per bit, whether it's QCA or anything else, you're going to have to pay a thermodynamic cost of this KT log 2, minimal, that's the floor. Our transistors now, of course, dissipate vastly more than that, many orders of magnitude more. So we could improve a lot, but you can't beat the cost of erasure. But it turns out it's a cost of erasure not, so to speak, a computation.
Thank you. Any questions from audience?
One has raised hand.
I think yes. I think
So general.
January.
Hi, good night, Professor Lent.
Hi.
So very to know you finally. So I have several years following your very interesting research. Basically, I have two questions. Do you have some physical implementations in the University of Notre Dame of these models?
Oh, I'll stop my share for this. So what we have are the metal dots. So we don't have chips, right? We have experiments that we've done. Again, I say we when I mean Greg Snyder, Alexei Orlov. On metal dots, we have molecules that we've shown these various parts working. We don't have circuits shipping chips or anything like that. It's very much research area.
So my next question is, do you consider, or is here some possibility to implement conservative computing with quantum dots?
By conservative, you mean, tell me what you mean
Right.
when you say conservative computing.
Bretkin gate, for example, Toffoli gate.
Oh yeah, sure. So any of the any such gates you can implement if you want to, and and they'll have the feature with these QCA cells, and they'll have the feature that since they're logically reversible, you can, if you operate them carefully with the clocking, you can lower the dissipation, the physical dissipation of heat as low as you want, which as you can, that's the driver for me.
All right.
Okay. Sir, I have some basics question actually.
Yeah.
In recent time, I have saw some paper on atomic clock, and I have find something that Landauer clock. So, what is the difference between the Landauer clock and Bennett clock according to QCA?
So the difference is the Landauer clock is it's kind of the normal clock. So you take an area. I have to wave my hands, so my hands have to be visible. You have an area that you turn on, and then you have the next area that you turn on, or you slide it smoothly across. Right. So I was trying to make a distinction between sort of the usual clocking like that, either by zone or smooth. The Bennett clock is a more costly business where you have to clock all the way, all the way across the circuit. I can't get it right. You clock all the way across, and then you clock all the way backwards. And it seems like a crazy thing to do. You first compute the output, and then you use the output to uncompute back to the inputs, keeping the outputs. So that's actually precisely what's done in the adiabatic CMOS analog. And when, not myself personally, but my colleague Greg Snyder at Notre Dame, when he built these circuits that could lower the power dissipation so much, he did exactly that. You have to have these clocks that's called retractile cascades of clocks that move across the circuit and then unzip. So I think I called those Bennett clocking to honor Bennett, who pointed out, Charles Bennett at IBM, that in fact you could embed any even logically irreversible process in a reversible process if you were willing to do that sort of thing. Hope that helps.
Bennett clock is indeed for very low power operation possible. That means a low power operation is possible in Bennett clock.
Yeah, so low power operation is possible with just regular Landauer clocking, standard clocking. But if you want to get the absolute lowest power, then you want to, and you're willing to pay the price of going forward and backward block by block, then you can do Bennett clocking, and that squeezes the last bit of dissipation out of the system. And you know, some people have said, well, take the inputs, all the intermediate results, and write them down on a, so to speak, write them to disk, so you never erase them. You just keep them around. That it just gets, to my way of thinking, that's extreme. You know, so you're already getting many orders of magnitude improvement out of doing this sort of adiabatic switching. But it's interesting to see that you can squeeze the last little bit out if you're willing to go that far.
Yeah. Thank you, sir. Thank you, Professor Lent, for this interesting and nice presentation and talk. Thank you, sir.
Quite welcome. Quite welcome.
Thank you, Professor Lent, for inviting our invitation. Yeah. Okay.
Pleasure to be with you all.
Yeah. Thank you. Thank you.
Thank you, sir.
I would, if the time difference weren't what it is, I would stick around for several more talks, but it's in Indiana here, it gets quite late and I'm old. So thank you very much for your attention.
Thank you, sir.